Welcome to our framework for action-oriented skill development, where learning is presented as a loop. A stimulus prompts an action, which then leads to a consequence and feeds back into reinforcement. The slide's diagram shows how observable measures, conditioning protocols, and a skill acquisition curve work together to optimize practice, track progress, and iteratively refine behavior for better performance over time. This slide introduces the pioneers who shaped behaviorism and the idea that learning equals measurable behavior change. From Watson's focus on observable actions to Pavlov's paired stimuli, Thorndike's law of effect, and Skinner's operant conditioning, each approach emphasizes frequency, latency, and duration as key metrics. The visuals tie these theories to data-driven evidence, reminding us that measurement is central to behavior-focused teaching. Here we look at classical conditioning and how neutral stimuli can become classroom signals. The diagram shows a neutral cue paired with an unconditioned event, so that over time, the cue alone elicits an automatic response, like attention or anxiety. Important concepts like extinction, spontaneous recovery, and stimulus generalization explain why signals work, fade, or reappear, and how teachers can deliberately shape classroom reactions. This page explains how reinforcement builds academic habits by increasing or decreasing the probability of behaviors. The slide differentiates positive and negative reinforcement from punishment and highlights practical tools like schedules, shaping, and chaining. By using these methods thoughtfully, simple actions such as raising a hand or complex sequences like multi-step math problem-solving can be reliably taught and reinforced toward consistent classroom habits. The chart on reinforcement schedules compares ratio and interval patterns and their behavioral effects. Fixed ratio yields high response rates with pauses. Variable ratio produces the steadiest, most persistent responding. Fixed interval creates scalloped bursts typical of cramming. And variable interval produces slow, steady effort. Examples like sticker charts, gambling analogies, scheduled quizzes, and checking email help explain why timing and unpredictability shape different response curves. This slide focuses on foundational skill automation using repetition, timed practice, and spaced review. The three-box flow shows repetitive timed exercises to build fluency, immediate feedback to prevent error chaining, and cumulative overlearning with spaced review to transfer skills to long-term memory. Practical examples include phonics, multiplication drills, and keyboarding, emphasizing that consistent practice plus real-time correction leads to mastery. Token economies are presented as structured reinforcement systems for group management and delayed gratification. The slide maps token acquisition, token exchange, and eventual skill development, stressing menu and ratio design, fading procedures, and measurable fairness. Whether using points, chips, or digital credits, the system teaches students how to save, trade, and earn privileges while reducing dependence on external rewards over time. This page shows how complex tasks are decomposed into stimulus response chains and refined through successive approximations. Breaking a skill into initial, intermediate, and terminal links allows targeted reinforcement at each step, while shaping moves learners gradually toward the final criterion. The visuals tie this to real-world skills like handwriting, lab techniques, and musical performance, illustrating a clear path from simple elements to polished mastery. The slide addresses key risks and critiques of a mechanistic behaviorist approach, treating learners as programmable, neglecting internal thoughts and emotions, and over-relying on extrinsic rewards that can undermine intrinsic motivation. It also raises ethical concerns around punishment and dignity. The point is not to discard reinforcement but to weigh its efficiency against psychological complexity, cultural context, and learner well-being. Here we trace behaviorism's evolution as cognitive and socio-cultural critiques, like Chomsky's focus on innate structures and Bandura's modeling, push the field toward integration. The diagram shows a resurgent interest in mind, self-regulation, and context, producing modern syntheses that retain reinforcement insights while embedding them in richer cognitive and affective frameworks for a more holistic understanding of learning. This slide reframes the Skinner box for the digital age, with gamification and analytics feeding a reinforcement loop. Instant badges, streak counters, and adaptive quizzes drive engagement while learning analytics measure response latency, accuracy, and deliver timely reinforcers. The slide also calls attention to ethical issues, data privacy, algorithmic transparency, and student autonomy, urging a balance between motivational design and responsible, humane implementation. The final slide explores AI-enhanced behaviorism for individualized learning and ethical deployment. AI can optimize reinforcement timing, adapt task difficulty, and fade supports to promote autonomy. But the framework emphasizes transparency, learner agency, and hybrid models that combine behavioral efficiency with humanistic care. In short, AI can augment the reinforcement loop, but strong ethical safeguards and clear communication are essential for trustworthy use.